So in this video, we're going to talk about continuous functions, polynomials, rationals, exponentials, logs, trig functions. These are all continuous on their domains. So polynomial like 5x cubed minus 7x squared plus 3. That's an example of a polynomial. Rational is basically we're taking two polynomials and we're dividing them, right? So that's rational functions. Those are defined on their domain. They're continuous on their domain. And what is their domain? It's where the denominator is not equal to 0, right? That's the domain of rationals. Domain of polynomials is from negative infinity to infinity. Those are real nice, smooth, continuous curves. Exponentials like e to the 2x or e to the x negative x squared, whatever, okay? 5 to the 7x, I don't know, just something, right? So exponential is where the base is fixed and the exponent is the variable. Logarithms, you know what a logarithm is, like log 3x, whatever. Okay, natural logs, ln, 5x, or whatever. All right, so logarithms are continuous on their domain. Exponentials are from negative infinity to infinity. Think about what an exponential looks like. Okay, kind of like this. Now so that's from negative infinity to infinity, right? Logarithms are the inverse function, so they're like that. So typically logarithms are defined for like x greater than 0, for like 0 to infinity kind of thing going on. Okay, so those are like logarithms. Okay, now trig functions, there's 6 different trig functions: sine, cosine, tangent, and then the reciprocal functions, cosecant, secant, and cotangent. Now trig functions like sine and cosine, those are continuous for all real numbers. But then you have things like tangent, which is a periodic function, and so periodically you see these vertical asymptotes, and so they're not continuous everywhere, but they are continuous where they're defined. They're on their domain. Okay. Now these are direct results from the theorems listed there. You can check those out in your book. But here's a theorem. Okay. So theorem 1.5.1, properties of continuous functions. So I'm going to let f and g be continuous functions on the interval I. I'm going to let c be a real number. So c is some number. And I'm going to let b be a positive integer. The following functions are continuous on the interval. Okay, so f plus or minus g is continuous. Okay, c times some function, f times g, f divided by g as long as g is not equal to 0, f to the n, the nth root, and that has to be adjusted if n is even, and composition of functions. We don't get too much into this, but adjust the definition of f and g to let f be continuous on I, or the range of f on I is j, and let j be continuous on j. Then g composed of f is continuous on I. Okay? Now, what is all this saying here? This is saying basically like if I know that f and g are continuous on some interval, then the sum and f of g are continuous on that interval. Okay? If I know that f is, so like if I had like x squared, which I know is continuous from negative infinity to infinity, right? And I had, I don't know, say square root of x. This is continuous from 0 to infinity. All right. Now, the sum or the difference of those two, Well, you think about it, where are they both true, right? Well, x squared is true everywhere. Now, the square root of x is only true for 0 to infinity. So where are they both true? Where do they both overlap? Well, they both overlap from 0 to infinity. So that would be the new place where they are continuous. So each individual piece needs to be continuous. Okay, so let's work through a problem. I think this is going to help. So give the intervals on which the given function is continuous. So we're actually given f of x, which equals the square root of x minus 2 plus 6 square root of 6 minus x. Okay? So with this problem here, all right, x minus 2, what do we know about a square root? Square root of whatever is inside here, that has to be greater than or equal to 0. Okay? So I set it to be greater than or equal to 0. That's how I find where its domain is. And when I get the domain, what do I know? I know that they're continuous on their domain. So we're not proving, right? All we're doing here is we're just figuring out where the domain is. And then since we know that it's falls into our category, square roots, continuous on their domain. Okay, rational exponents. All right, so give the interval on which the given function is continuous. So if I solve for x, x has got to be greater than or equal to 2. So in interval notation, that looks like this here. All right, and so if I graph this, well, greater than or equal to 2 means I'm going to shade to the right. Okay, so I shade to the right this way. Now I need to focus on this side over here. Well, I see the 6 here, so I'm probably going to have 6 going on in here. I take what's inside, and I set it to be greater than or equal to 0. Okay, it's not set equal to 0. I see that's the biggest mistake I see people make with these problems when they're trying to find the domain. They just set the inside of the square root equal to 0. That's not what you're doing. The reason I set this to be greater than or equal to 0 is because it's a square root, it's an even index. That means whatever's inside here has to be non-negative, okay? I can't take the square root of a negative number and get a real number, okay? So if I solve for x, I move the x over, add x to both sides. I have x less than or equal to 6. And so shading that in interval notation, looks like this right here. So I'm probably going to want you to write interval notation for your final answer, and then you can graph it. And when you graph it, you see that there is an overlap. Okay, that overlap goes from 2 to 6. And so my domain here for this function only works for 2 to 6. Anything outside of here, it only works for 1. Okay, so it's got to work for both of them, right? So if it doesn't work for both, then you're kind of stuck. Okay, so it only works for both from 2 to 6 here. And therefore, that's where the function is continuous, from 2 to 6. Okay? So a little bit different when we're proving continuity over an interval versus proving it at a single point, x equal to c. This is more of the hand-waving approach. You take real analysis or introduction to analysis, whatever. You're going to be able to prove this by mathematical definition. So that's more of a senior level math course or a junior level math course than a freshman or sophomore. Okay? So let's work on the next function. G of x equals the square root of the natural log. Ooh, that's kind of flip out, right? Well, what do we know first right off the bat? We know whatever's in a square root needs to be greater than or equal to 0. Okay, so I set it greater than or equal to 0. Now, how do I solve for x here? Well, I have to think about what the inverse function is. What's the inverse function of ln? The inverse of ln is e to the x. So when I'm going to raise both sides, I have each one, I have e to whatever it was before, right? Now the e and the ln cancel each other out, so I just get x on this side here, but e to the 0 is equal to 1. So what does that tell me? That tells me that x needs to be greater than or equal to 1 for this to be defined. And because it's on the domain, that means that we're continuous on this interval from 1 to infinity. Okay? So that's kind of how you work at it. We use this property a couple of times here in these problems. If n is even, I have to require f of x, this function inside here, the square root, right? I have to say that that's greater than or equal to 0. Okay? So a little bit of hand waving there, but this theorem allows us to do the hand waving. So if f and g are continuous functions on an interval, then let c be a real number and n be positive, and the following functions are continuous. Okay, so we just are basically, we're talking about individual pieces in here, and then what we're doing is we're taking, it's like these polynomials here are continuous everywhere, right? But as soon as we introduce that square root, this rule falls into play, and by golly, we got to make sure that those square roots, the inside part of them, the radicand, is positive or non-negative. Okay? All right. So in this example, we're going to determine if f is continuous at the indicated values. So this one, we're actually going to fall back on our definitions. So we're given particular values. So how do we find that f is continuous at a certain value? Well, what do? We look at this. We have to show that the limit exists, meaning that the right and the left are equal to each other. We have to show that f is defined, so it equals something. And then we have to show that not only is it defined and the limit exists, but those two things are equal to each other. So if you show those 3 steps, then you got it. Okay, so let's do that with this problem here. Okay, so the first thing I'm going to do is I'm going to check it for a equal to 0. So what do? I take the limit as x goes to 0 here. Okay, and when I do this, well, let's see if it exists. Well, why does it exist here? Well, at a equal to 0, what part of the piecewise function am I on, right? So 0 is less than 1, so we're not here. So that means that we got to be using this function right here. So anything less than or equal to 1 falls into that category. Well, a equal to 0 is clearly that part right there. So this is the function that I'm dealing with. So when I take the left-hand limit, I'm going to take that limit as x goes to 0 from the left of x minus 1. If I plug in 0 from the left, what happens? I just get negative 1. Okay? Now I'm going to do the limit from the right. The right side is 0. I'm still going to be less than 1, right? I'm looking at values that are barely bigger than 0. That's clearly less than or equal to 1. Okay? And so I'm still using the same function here. And when I plug in 0, I get negative 1. Well, lo and behold, since the left hand and the right hand limit exist and they are equal to the same thing, then that tells me that the limit exists. So that's what I'm looking for, guys and gals. Now, the second part, we got to determine, is it defined here? If I plug in 0, what am I going to get? If I plug in 0, I'm going to be on this part right here. So I plug in 0, I get negative 1. So it's defined, check. Okay, the last one is, what does the limit as x goes to 0 of f of x equal? Well, since we know that the left-hand limit is negative 1 and the right-hand limit is 1, we can say that this equals to negative 1, just like those did. And guess what, guys? That negative 1 is equal to the function value, and this is exactly what I wanted to prove here. So if you wanted to add in one step in here, you could say, you know, that this is equal to -1, and then that's equal to this right here. Okay, so that kind of tells me that I know you know what you're talking about. Okay, so with this one here, f is continuous at x equal to a, or at a equal to 0. Let's try it out for a equal to 1. So this one's going to be a little bit more interesting because 1 here happens to be, you know, where our piecewise function switches from being a linear function to a quadratic. So maybe it connects, maybe it doesn't. You can definitely tell if you just graph this thing, okay? So the fastest way to figure it out with a piecewise is I take a left-hand limit and a right-hand limit. Okay, if they don't match up, then we're done, right? So if I do the left-hand limit, which side of the piecewise am I on? I'm on the side where I'm talking about values of x that are less than 1. So that's like 0.99, right? And so that's definitely going to be less than, so I'm dealing with this part of the function here. So I'm going to replace f of x with x minus 1. And whenever I plug in a 1 here, I get 1 minus 1, which gets me 0. So the left-hand limit is 0. Okay? Now the right-hand limit. The right-hand limit, that's values that are like a little bit bigger than 1. A little bit bigger than 1 is going to be this top part of the function here. So I'm going to replace f of x with x squared. And whenever I plug in 1 for x squared, I get 1. And so what does that tell me? That tells me that the left-hand and the right-hand limits are not equal to each other. Therefore, the limit does not exist. And if the limit does not exist, that contradicts the very first rule, which says that the limit needs to exist for f to be continuous at that particular point. And so therefore f is discontinuous at x or a equal to 1. Okay, so that is what I'm looking for, the write-up, when you're doing your answer here. And like I said, if you wanted to add in that little extra step of saying this is -1 and that's equal to that, that's fine. As long as you have all this written out, you're good to go. Okay? So that concludes and hopefully sheds a lot more on how to prove that it's continuous at a single point, and then how to prove it's continuous on some interval whenever you know you're dealing with polynomials, rationals, exponentials, logs, trig functions, etc. like that, right? Those are all continuous on their domain. So all it amounts to is finding the domains. But if it says to find it at a particular point, what I will not accept is you just saying, well, look, it's continuous. It's continuous for polynomials, and these are polynomials. Therefore, it's continuous at x equal to a. That's not going to work. Whenever I ask you to prove it at a single point, what I'm looking for are these three things here. But if you're given some function here, then I'm saying, you know, tell me where the whole function is continuous. You can't say, okay, say even if it is just 2 to 6, right? How do you prove it for each point? You work on, okay, I'm going to prove it for x equal to 2. Okay, well, then I'm going to prove it for x equal to 3. Well, what about 2.5, right? Or what about 2.4? What about 2.00001? You see what's going on? There's an infinite amount of numbers between 2 and 3. Okay, so it's crazy, like, to try to prove it on some interval, right? So that's why we have this theorem here to help us out. And like I said, when you get to Introduction to Analysis, which is beyond the scope of this class, then you will learn how to prove this mathematically on an open interval. Okay? All right, guys, so that concludes this video. Hopefully